Okay. So last time we mostly focused on limits graphically. We looked at the picture and said, do our limits exist or not? Today we're going to talk about a couple of other different ways. So let's look at this one. Limit as x approaches 1 of x plus 1. Instead of creating a picture for this and finding the limit from a picture, this time let's try and find the limit what we call numerically. Let's find it making a table. So numerically is just a different word for table, making a list of information. So I want to make a table that tells me what my limit is approaching. But remember, we're just like Ben said, we're never actually going to hit 1. We need to just get really, really, really close to 1. So what can get me pretty close to 1 from either side? What number is pretty close to 1? Not over. That's from approaching from the right, 1.001 or 1.01. So let's say approaching from the right. Let's start with 1.1 and then get closer, 1.01, 1.001. What about from the other direction? 0.9. So we're just trying to make sure, and the reason we're taking a couple of values and not just doing like 0.99999 is remember, we have to make sure it's following a pattern. Limits are about what happens as we're approaching, so we have to check as it's approaching, not just what's close to it, but what's happening pattern-wise as we're approaching this. So if our function is x plus 1, how do I find for our table that y value at 0.9? How do I find its associated y value? It's f of x, because remember this section is f of x. Is x plus 1. How do I find y values? Plug in x. So we plug in 0.9. We plug in 0.9. What should we get? 1.9. 0.9 plus 1. 1.9. What about the next one? 1.99. So it's a pretty easy one to plug in. Or 1.999. We're skipping over 1 because remember we're just trying to see what happens as we approach. So as we approach, what does this look like it's getting closer to? 2. So now we say, okay, it's getting close to 2. Let's check what's going on from the other side and see if that's also happening. For limits, we have to approach the same thing from the left, same thing from the right. So from the right, if we plug in 1.1, what do we get? 2.1. 2.6. So as we approach from the right side, what are we getting closer to? 2. So if we approach the same thing, what did we say that means about our limit? It is 2. Our limit is 2. So this is another way, and it's not used as often as the graphical method or what we're going to call the analytical method in a second. But it's still good to be able to read this information. It's just like what we did when we were looking at the graphs. We said as I get closer and closer, what am I getting close to? Same idea, except we're actually finding numerical values to go with each time we look closer and closer. So our limit right now looks to be 2. So this one obviously doesn't have any, we have x plus 1. What kind of function is x plus 1? What would it look like if we graphed it? Plug it into your calculator if you don't remember. Ben, do you remember?
Let me just go like this.
So what do we call that? A line. X plus 1 is a line. Anytime we have the variable x with no, it's not x squared, it's not x cubed, it's just x, we have a line. This is a line. So if it's just a line, we're going to have any weird things going on, holes, jumps. No, just a plain old line. So since there's nothing weird going on right now, let's look and say, okay, what if I did want to figure out what was going on exactly at 1? Would that help me find my limit? So what would happen if we found exactly what was going on at 1, if we plugged it in? What do we get? 2. So did that value match our limit? Yeah. So that's the analytic method. When we're taking limits, if they don't have any weird things going on, if they're what we call a continuous function, we'll talk more about what continuous means next time, but basically it means no holes, no gaps. It's just, it can still be a quadratic, but that has no holes, no asymptotes, nothing weird is going on. I can plug it in. If I take my limit and I just substitute x with 1, I get my value of 2. So this is what we call this the analytic or algebraic method. And basically, all you do is plug it in. So if we're using the analytic method, plug it in. And there will be some instances where we can't do that, and we'll learn about those instances. But the basic is, if you can plug it in, plug it in. And that finds the limit. Because a lot of the time, the limit itself is the y value. Not every time, but for most nice functions, our limit is the y value. Okay, so what about this one? What if I'm taking the limit as x approaches 6 of 3? Kind of don't like the way this equation editor wrote it. The 3, in my opinion, is too close. 3 is to the side, kind of. So I want you to talk about that with your groups really quick. What do you think this limit would be? Remember, we're trying to figure out y values. What y value would we be approaching as x gets closer to 6? So I'm going to give you just like 1 minute to talk about that. At your 2. What did everyone think? 3. So we're trying to figure out y values and what we're approaching. What would this look like if I said y equals 3? What does that look like as a graph? Horizontal line at 3. So, what if I asked you the limit as x approaches 100 of this?
100?
Still be 3.
No, just kidding.
What if I asked limit as x approaches negative infinity of this? Still be 3. We're trying to determine y values. Well, this function has the same y value every time. I guess I should be a little more specific. We're trying to figure out what y value we are approaching. But still, this approaches the same y value no matter where we're at. I could ask you what the limit is as x approaches pi. It would still be 3. Okay? So, because there's nothing to plug in here, if we don't have an x value, it's just the constant itself. So now we've learned a new property. I could put this out as a mathematical property. I could say the limit as x approaches c of k, where k is an integer, or a real number. That is what I was searching for. Then it would just be k. It would just be the real number that was already there. So now we come to one where what would happen if I tried our new analytic way? What did we say we should do if we have a function and we're just approaching some number? What should we try first? Plug it in. Josh says, let's plug it in. So let's see what happens when we plug it in. If I start with 2, plug it in everywhere I see x. What happens? 0 over 0. And what did we say happens when we divide by 0?
The earth implodes.
The earth implodes. Life as we know ceases to exist. We can't do it. So we need to figure out some other way. We have a problem here. If we can plug it in and it doesn't give us a problem, we're good. But if we plug it in and it gives us a problem, we have to think through and say, can I change this anyway so the earth does not implode any longer? So looking at this function, is there something I could do to switch around or rearrange things, rewrite things? I think it's on your lips, Emma. Okay. She said, well, let's try factoring. What can we factor? Can we factor the top one or the bottom one? The bottom one. The top one doesn't factor because we would need, in order to factor, we need a common something that's multiplied into all of it, or it needs to be a quadratic. Which is 2. So the top one we leave alone. It does not factor. Factor the denominator. We have to think back to our Algebra 2 / pre-calculus skills. We know x squared has to break down to be x times x. We know 2 has to break down to be 2 times 1. We just have to figure out signs at this point for this one. If I need to get a -2, what do we know about these two numbers? 1 has to be negative, 1's positive, 1 is negative. And if we know the middle number is negative, we know the bigger integer has to be that negative sign. If the middle number was plus 1x, then we switch the signs. It'd be -1, +2. So now what happens? Okay. What would happen if we plug it in again? If we have 2 minus 2 over 2 plus 1 times 2 minus 2. Okay, so we still have 0 over 0. So good idea, but it's still not quite where we need to go. What's something else I can do? What if I had 3 over 2 times 3? What can I do to simplify this? Take out the 3. Okay. That just leaves me 1/2. Well, this is the same idea. Even though they're bigger terms, what's the same? Okay. The x minus 2 and the x minus 2, they can cancel each other out. We can't forget there is still a 1 in the numerator. Usually what students want to do is they want to just take x plus 1, that's my final answer. But x plus 1 is in the denominator. We can't move it up to the numerator. Okay, so now what should we do, Emma?
We should plug it in.
We should plug it in. Now we can plug it in because it's not going to give us trouble anymore. What's my limit? 1/3. So this is just one of the instances where there's a couple of different types of instances where the limit, we have to kind of do some rearranging before we can get to here. And this is the most common one you'll see on like the AP Calculus test. If they were to ask, limit questions are very few and far between on the calculus test, but they're so essential to derivatives, we still have to spend a good amount of time on them so that we can understand a derivative really well. Even though individual limit questions won't show up very often. So that's the one we'll focus on, and I think that's the only one I gave you a homework assignment on, a homework problem on. But just so you see what some of the other options are of how we would have to rearrange things. I don't want to screw up writing these down, so I'm going to steal them from the book. What if instead, and we're not even going to go through the whole problem, just give you the general idea of how you would deal with it, so you don't have to write these down if you don't want to. They're good to know and good to know how to deal with, but they're not so important for the AP test. I feel we need to really focus on them. Okay. So if we plug in 0, we get 0/0 again. The world implodes. This time factoring's not an option, it is factored. So what do you think we should do instead? I've got to rewrite something. What's the most complicated thing right there? The cubed part. 2 plus x cubed. So that's our most complicated thing. What's something I could do to rewrite that? What does cubed really mean?
You could have it squared and then times that by 2 plus x.
Okay, let's take that one step further. What could we do instead of writing it squared?
Just have it 3 times.
Have it 3 times. That's what cubed means. So if we multiply that all out, like I said, we're not going to focus on it enough to really spend time going through the whole problem. But if we multiply all that out, it's going to cancel out with the other 8 here. This 8 would cancel with what we get when we multiply that out. And then we can divide our x into each of them, and you'll be left with something again where we can plug in 0. So once again, it's not something you're likely to see on the AP test, but just so you kind of are thinking again of different ways to handle different situations. Okay, so here's a second option, something that's a little bit different. Once again, we're just trying to think of ways to deal with a situation like this. He's very loud. What could we do with this? This one's even weirder. Again, look at it. What's the most complicated piece right now? What his foot looks like on the inside too?
No, that's the pump. I'm doing the surgery.
Okay. So what's the most complicated part of this expression? 1/2 plus x. There's this fraction here. Okay. Well, I can't really simplify just that fraction. But what can I do if I have 2 fractions subtracting together? Can you say that louder, please?
You could find a common denominator.
Okay, you can find a common denominator. Now this is what we call a rational expression. We can't just, if you have 1/3 and 1/2, it's obviously 1/6. But it's the same idea. If I had 1/3 and 1/2 instead of 1/2 plus x, how do I find the common denominator with these two things? Multiply. 3 times 2. Same idea. These two multiplied together would be my common denominator. So I have to multiply by 2 here, which means I would have to multiply by 2 here. I have to multiply by 2 plus x here. And once again, we'd have to combine things and rearrange things. This one, I think it's good enough to see some of the fractional stuff. I think we're going to keep going on this one, because you do have to do a lot of fraction work, and that can sometimes screw you up with the rest of calculus. So if we have, and I cannot stop writing this limit out front until we've actually plugged in 0. I know it's annoying. We know that that's what the problem is asking us to do. But for the AP test and for getting points on the free response problems, we need to be very particular that we're not just leaving off math notation that hasn't stopped being used yet. So if we multiply this out, we get 2 over, and I'm going to leave it as 2 times 2 plus x for now, minus 2 plus x over 2 times 2 plus x all over x. So now we can actually do the subtraction in the numerator part, in this part. We would have 2 minus 2, which is 0, but we also have the minus x, so we get, I always do that. I don't know why I want limit to have a line underneath. So we get negative x over 2 times 2 plus x over x again. So this is the part I really wanted you to see, just to practice some fraction stuff. Okay, what if I have a fraction like this? What's going to end up happening?
Multiplied by the reciprocal, right?
Okay? So I always write it old school, because when we say multiply by the reciprocal and it's all stacked like this, I have no idea what the reciprocal is. So for me, at least, the way my brain works, and a lot of students' brains don't work this way, but for me, I have to write it old school in order to see what's going on. I need to write my main fraction divided by x. And that way I can see, when I change it to multiply by the reciprocal, which part I'm actually flipping. So once again, it's personal preference. If you can see what's going to happen with this x without doing that, more power to you. But for me, I need to write it out with this old school divide sign, so I can say, okay, this is going to change to times, and this is going to become 1 over x. So that helps me with my fraction division. And then we could simplify again. What would cancel on this one? The x. And then we could plug stuff in. So like I said, I didn't assign any of these last two. They're just to show you what they would look like and have you see them. The problems themselves would probably not be on the AP test, but just so you can see how these different situations can come up, and you have to view them all from different perspectives. Okay, so on this one, we're computing the limit. You can just, substitute in, but I also wanted to show you how the Inspire can help you check your answers and whatnot. We actually have a limit button on the Inspire. So we need a calculator screen. Right now I don't have a calculator screen. I'm just going to go to my scratch pad. So either get to a calculator screen in your document, or if you hit the scratch pad button, it gives you a calculator page, you just can't save it. So if we want to actually use our calculator to find the limit, we go to Menu, and you'll notice there's a Calculus menu, number 4, and there's a limit part. Okay, and it lets you enter it in exactly as it's written. Okay, so we have x approaching, it was 0, so we have to scroll over 0. So you'll notice there's a spot above the 0. It can also, you can compute limits from the left and the right, and we'll talk about that in a little more detail today. If you don't care whether it's from the left or the right, just leave that blank. And we had e to the x times cosine x, I believe, on the other page. It doesn't really matter so much. So go to trig, cosine x, and we hit enter and our calculator will. And it will even deal with those ones that have weird things. We could take that one we did where we had to factor, and we could plug it in, and it'll still find the limit for you, even though if we just went to plug it in, that would be a problem. So we go back to Menu, Calculus, Limit. Here's x approaching 2. 2. And we need a division. I think, I'm going to try this really quick. I think if you hit Control Divide, it already gives you a fraction. Yeah. Okay, and that way you don't have to go through that whole menu. I know it does a lot of cool things. So we had x minus 2 on top, and I don't know why x did not type in. And then on bottom we had x squared minus 2x. No, minus x minus 2. Sorry, I'm trying to remember this from memory. So in order for us to solve this, we had to factor. Our calculator should just give you the answer. Yay! So I show you this not so you'll go automatically to your calculator. It's a tool to help us, check answers, make sure we're doing things correctly. But we need to know both. When you take the AP test, there's a calculator portion and a non-calculator portion. So we need to be able to solve this both using our calculator and knowing that, hey, I would have to factor this and cancel stuff out and plug stuff in. But just so you can see the capabilities of the Inspire and why I wanted to use them. So this one, what did we get? We plugged in 0, 1. E to the 0 times cosine 0 is 1. So I could have also maybe made a table. What numbers would I pick if I'm approaching 0? What numbers would I pick so I get close to 0? 0.1, 0.01, 0.001. What about in the negative direction? This one always throws me for a loop. We want it to be negative 0.9, but that takes me close to negative 1. Negative 0.1, negative 0.01, negative 0.001. So we could find this using a table. I could instead draw a picture. I could draw the picture of e to the x cosine x and see what's going on at 0. So remember, there's those 3 different ways to solve a problem like this. Okay. So properties of limits. The AP Calculus test, the reason, most of these you kind of get the feel for as you're working with them, but the reason we talk about them specifically is because the AP Calculus test likes presenting you with so many different ways to do the same thing And even though they probably won't do properties of limits, I have seen problems with properties of integrals and properties of derivatives. So it's good to get an idea of how we work with them right now. So with our limits, the specific properties are in page 61 and 62. Writes them out in a little more detail. But it's basically saying you can take two limits and you can add them together and still get the same answer. You could take two limits and subtract them and still get the same answer. You could take two limits and multiply them, still get the same answer. You could multiply it by a constant and still get the same answer. You could divide them as long as what you're dividing by is not 0. Remember, 0 is bad when you're dividing. And you could raise it to a power. So for example, we're not going to write every single one out. But if I said the limit as x approaches c of f of x plus g of x. Okay. And sometimes we put parentheses around the whole thing just to show that the limit is applying to the whole thing. Well, what we're saying with the properties of limits is I could do that all together, or I could separate them and apply the limit to both. I could say the limit as x approaches c of f of x plus the limit as x approaches c g of x. And we would get the same answer, whether we added the stuff together first, or whether we took the limit first and then added the limits together. You still get the same answer. Ooh. I want to move on to the next page until everyone's done writing this down. Pause for a second. And we already wrote one of the properties down earlier, limit as x approaches c of k is k. And we had just a constant, the constant still. Okay, so this is where we would use just the properties of limits. For the most part, we just know that we plug it in. But they might give it to us in a really general form. So I don't even know what the function f of x is, and I don't even know what the function g of x is. All I know is x approaches 3 is that the limit of f of x is 4, and as x approaches 3, the limit of g of x is 8. So this is an actual example. I recommend writing this one down because you will have some homework problems that relate to this. So they would give you this setup information. They would say, we know that the limit of f of x is 4 and the limit of g of x is 3. What do those two things have in common, though? And it's very important they have this thing in common.
They approach the same
They approach the same
x value.
x value. It has to have that approaching the same thing. For all the properties of limits, it's always x approaching c, because they have to approach the same thing. If one said 3 and one said x approaching 5, then we couldn't do any of the things we're about to do. So part A, we want the limit as x approaches 3 of f of x plus g of x. What this is saying is, if I know the limit of one, we can add it to the limit of the other. So what's the limit of the f of x piece? 4. What's the limit of the g of x piece? 8. So our limit of the entire thing is 12. So we can basically do that with any basic operations, addition, subtraction, division, multiplying by constant, multiplying. So what would my next limit be? 1/2. She already reduced it. Limit of just the f of x piece is 4. Just the g of x piece is 8. So our limit is 1/2. And I know it seems so basic that you're like, why are we doing this? We're trying to get the foundation so when we do get to the more complicated ones, hopefully it's stuck in our mind that these types of things are possible. What about the last one? Yep, I heard someone say 32. We have a constant 2 times f of x, so the limit of f of x is 4. Limit of g of x is 8. So multiply those out, add them together, and get 32. So we've kind of have the general idea of what a one-sided limit is, and we've talked about for a limit to exist, it must approach the same value from both sides. But let's talk more about the notation and what we really mean by a one-sided limit. So when we talk about a one-sided limit, we focused on the graphs yesterday. We can either approach from the left or approach from the right, and we said, well, these have to match in order for us to have a limit. Well, notation-wise, if we're approaching from the left, we put a little minus sign above the number we're trying to approach from the left. All this is saying is approach from the left. So what's our notation going to look like if we're approaching from the right? A little plus sign instead. So we already know those have to match for a limit to exist. But they can exist on their own as well. We can approach from the left, get one number, approach from the right, get a different number, and then have the limit not exist overall. The limit as we approach 3 itself has no limit, even though these individual ones might have a limit. They just have to, they can still exist independently, but they have to be matching in order for us to have a limit. So we have a graph here. It's going to be the same graph for the next 3 things we talk about, so you don't have to draw it over and over again. You only have to draw it once. We're going to check the limit from the left, the limit from the right, and then then the value of the function itself, and see if we get a limit overall. Okay, so limit from the left. We don't care if the y value exists. It really helps us when it exists because that's when we just got to plug it in stuff. But it doesn't have to exist. So as we approach from the left and we're approaching the x value of 1, So here's everywhere our x value of 1 exists. Those are all x value of 1. We're trying to see what happens to the y value as we get close to that red line. So as I approach the red line from the left and I can only travel on my graph, what y value are we getting close to? 0. So my left-hand limit is 0. There we go. What about from the right? As I travel on my graph from the right and I'm approaching the red line, what's my y value getting close to? 1. So if I have a left-hand limit of 0 and a right-hand limit of 1, does my limit exist? Why? Okay, so Emma said no, it doesn't exist because it approaches different y values. So if we said the limit as x approaches 1 without the little negative and plus sign, our limit does not exist. Now, none of those things have to do with our y value. Our y value might match some of it, our y value might not match some of it. So in this case, what is our y value of this particular function? 1. That's where our hole is filled in, so it's 1. So it happens to match the right-hand limit, but it doesn't have to. Our y value does not have to have anything at all to do with our limits. It can, but it doesn't have to. So same graph, you don't have to draw it again, I just wanted it to still show up on each page. Now let's look at what's happening as we approach 2. So from the left, what y value am I approaching? 1. From the right, what y value am I approaching? 1. So what does that mean about my limit overall? That means since we're matching, the limit overall is 1. What about my y value at 2? This time our y value is 2. Our y value had nothing at all to do with the limits. It can, but it won't always have to match the limits. I think I'm going to skip the next one. I think you guys got the idea for this. So it's important to know how to find a limit, but it's also important to know when will a limit not exist. And we've seen one case over and over again, and it's the most common case. So what's the most common case we've seen of limits not existing? They approach different y values. We call this a jump. And it can exist everywhere else on the graph. It only doesn't exist at the jump itself. That's the only place where our limit does not exist, is at that jump. Or if I don't put arrows on these, if they just stop, our limit doesn't exist if there's no domain for us to talk about. But that's kind of a given. The second one we've seen is a vertical asymptote. If we have a vertical asymptote, our limit does not exist at that vertical asymptote.
And the last one again is one you don't see very often, but it's still good to know about. It's called an oscillation. And this one's kind of hard to draw and still get the full concept of it. It's like we have, and usually it happens at 0, but it's like we have a line we can't cross again. It's like we have a vertical asymptote, but it's not going to follow the same properties we know about vertical asymptotes, but we can't cross this blue line. So an oscillation only happens with a trig function. And what happens with an oscillation is with our trig function, it's going to start getting tighter and tighter together. And usually it gets smaller too. So the key about an oscillation is I can't keep drawing as many oscillations as there are. There's an infinite number of oscillations as we're getting closer. I could pick from 0 to 1 and I have an infinite number of oscillations. I could pick from, I guess, negative, or on the negative side. We could pick from negative 0.5 to 0, and we still have an infinite number of oscillations. This, we can't physically actually draw. We just have to know that this means it keeps going, bouncing up and down, up and down. If we zoomed in, it'd still be bouncing up and down. It's not actually stopping bouncing up and down. We just can't draw it anymore. And then the right side looks the same. So the reason a lot of people think they connect at some point, but it's not the case. There are infinitely many number of oscillations as we approach 0. So those are the 3 cases where a limit will not exist. Those are the 3 things we have to watch out for a limit to not exist, or like I said, domain. If our function doesn't have a domain, a good example is a square root function. If I said square root of x, once again we have to think back to pre-calculus, what's that look like? Sideways parabola, but more specifically, we only take the top portion. If we took the bottom portion, it would be a relation, not a function. What's the domain of this? Where does this exist in the x direction?
From 0 to positive infinity.
0 to positive infinity. So if I asked what's the limit as x approaches -5, there is none. We have no limits on the other side. What if I said the limit as x approaches 0? What did we say has to happen for a limit to exist? What's the requirement for there to be a limit? Both sides have to approach the number. Well, what am I approaching from the right? 0. What am I approaching from the left? There's no domain. So this does not exist, even though I could plug in 0. That's why we want to make sure we don't just jump to the plug-in all the time. We have to make sure we're thinking critically. I could plug in 0 and get 0. If I said the limit as x approaches from the right, I could do that. I could say, well, square root of 0 is 0. So it's a small, subtle thing that you have to be on the watch for. AP people love the small, subtle things that try and trip you up. I don't know why, but they do. They're not always super straightforward with this test.
That's kind
Okay. So 2 things we just have to memorize. I think this should be, the last slide. Tell we're fading. Ready to be done. Happens, it's 4th period. Okay, these 2 limits you should just have memorized. Usually the first one is more important. So with these, we need to start getting our 3x5 cards.
wrote it on the board, but I don't think I've ever said it out loud. I would like you guys to bring in some 3x5 cards. Because we have a lot of things to memorize, so we're going to start making flashcards for everything we need to have memorized. And these would be our first 2 flashcards, except that I kept forgetting to say bring some 3x5 cards, so we'll make them next time. So bring in some 3x5 cards. These we just have to have memorized.
Limit as x approaches 0 of sine x over x equals 1. And limit as x approaches 0 of 1 minus cosine x over x is 0.
There is a way to prove these, but it's called the sandwich theorem. And you do not have to learn the sandwich theorem for the AP test. So we'll just leave it at memorizing and not prove why these are true. Unless you want me to. I like proving things. I think it does show in the book. It does say the sandwich theorem, but I don't know if it applies it to these. No, it does not. So most of the time they're not just going to outright ask you, what's the limit as x approaches 0 of sine x over x? They're going to make it a little more difficult than that. So what if I said the limit as x approaches 0 of tan x over x? Once again, we have to be a little flexible. When we had x minus 2 over x squared minus x minus 2, we said, okay, I've got to rearrange this somehow. I have to rewrite some things. And we showed a couple of other instances where we had to rewrite and rearrange things. So algebraically, or I guess trigonometrically, first we're not even going to use any calculus. We're going to just say, what's something I could rewrite in this equation? What's something I know can be written as something else? Anyone remember what tangent x can be written as? Sine of x over cosine x. There's actually another one. What's another one? Back to our trig days. 1 over something. 1 over cotangent. Okay. I'm going to get you a paper soon of just trig things that you should know from last year. So just kind of a reference sheet. Okay. The most useful one for us right now, though, will be sine over cosine. So we know tangent is sine x over cosine x. Once again, I have to write things old school when it comes to fractional division. So if you can understand, hey, if I put a second line here, divide by x, and know where that x is going to go, then you can write it out. But for me, I have to say, okay, we know tangent became sine over cosine. That's one fraction. We're dividing by x. So that means, really, we're multiplying something. What are we multiplying by? 1 over x. So we're getting closer to what we want. Which one is this like of the things we're supposed to memorize? Sine x over x. So when we're multiplying fractions, I can rearrange the top however I want, I can rearrange the bottom however I want, and it's still true. So I'm just going to switch the cosine and the x. And then according to our properties of exponents we learned, I can take the limit of each piece individually. What's the limit of sine x over x? 1. That's our new thing we have to have memorized. So really what I'm doing is I'm taking the limit of this first piece. You don't have to write it out like this, but just to show you what's going on, times the limit of the second piece. 0 cosine. Ah.
So this whole thing we know is 1 because I told you so. Like I said, I could prove it if you want me to. But I'd have to prepare the proof again. I'd have to look at it. I don't know it off the top of my head. And then the other one, limit as x approaches 0, 1 over cosine x. What should we do to solve that limit? What's our first way to try every time to see if it works? With limits. Plug it in. What's cosine of 0? I know, we hate trig, but we do need to know this off the top of our head. What's cosine of 0?
Zero.
Good guess. We know it's one of the two.
1.
1. I always have to, for trigonometry, I'm remembering cosine of 0, sine of 0, I always have to think of the graph. We know cosine goes like this, and sine goes like this. So that helps me remember cosine of 0 is 1, just by thinking of the graph. Or I remember my unit circle. We know unit circle goes cosine, comma, sine. So this point on my graph is 1, comma, 0. Cosine is 1, sine is 0. So 2 different ways to help remember those trig values. Okay, so here is our homework assignment.